This video is from my earlier course, back when I was building out these ideas. The fundamentals I cover here are still solid, but the frameworks have evolved significantly since then. Head to systemthinkinglab.ai to see how this turned into a full course series. Hello, and welcome to the next lesson, storage, zeros and ones stored in a useful structure. Let's get right into it. So what is storage? Storage is data, zeros and ones, organized in a particular way to save information. This particular way is typically described by one or more data structures. Now, why care about data structures? Now, especially, the key audience here are junior, developers, junior engineers, and you either been through computer science courses or a boot camp, or you self-taught and you learned about data structures and what they are. But what we're going to go into, today, what we're going into this lesson is some of the groupings of data structures that are out there and how they provide the ability to provide functionality that is critical for systems to function, to operate, and to operate within each other. So it is very important, it is very critical to understand data structures because they're actually at the core of how systems are built. Because raw binary data is not inherently meaningful by itself. Storage using data structures provides shape and context to these bits, these zeros and ones. An efficient organization of this data improves retrieval speed, how fast you can get data, memory usage, how do you use the memory that you have, and ability to scale complex systems. You'll be surprised that you might use one data structure for a particular system, and as it scales, as there's more traffic or people use it more, you may have to shift to another data structure in order to handle the load. Understanding the trade-offs, understanding the things that you need to do, the benefits of one data structure over another is critical to be able to understand and design systems. So I have three categories, essentially. Again, this is somewhat simplistic, because data structures is a very rich field. There's lots of different and very innovative ways that we can do data structures. But remember, the goal of these sets of lessons, the goal of this course, is to provide that senior level intuition to junior engineers. And when you will find as you become more and more senior is that yes, you might understand more on some of the more complex things out there, but the more usable insight is you understand that a lot of these new problems that we have, we can use the stuff that we understand before in order to build them and to build them more efficiently. So understand how things are related to each other is critical to understanding how to design systems. So let's break down these, lots of these data structures into three categories. So first categories, I have the lists, the arrays, and the vectors. It's a linear sequence of data, elements that are stored in a specific order, often indexed by integers starting from 0, and they can be extended to multiple dimensions, 2D, 3D, etc. So arrays are multi-dimensional structures. You'll have a 1D array that can be a simple list. 2D arrays, think of a spreadsheet, think about Google Sheets, Microsoft Excel, that with rows and columns, that's just a 2D arrays because you think of it as an array of an array, right? Array of arrays, basically. And then there could be higher dimensions, 3 or even beyond, that are useful in advanced applications like matrices and math and tensors and machine learning and so on and so forth. But it's always it's important to have this insight of arrays. And just to undercoat what a typical array would end up being, essentially you're looking at just if you have let's say, you have that A, B, C, and D example that we have right here. I'll just circle it. Hold on. I'll just circle right here, right? That I'm referring to. So the order matters here, right? So, sorry, give me a second with this. 0, 1, 2, 3. So essentially you have the ability to access those elements by the index, starting with 0. So if you want to say this array at index 0, boom, that's A. At 1, there's B, and so on and so forth. Why is this important? Typically, arrays are stored in memory in the order that you see it in. So literally there's like a mathematical equation that's telling you, oh, okay, if you want to get to B, you go from the start memory location of what A is and multiply it by how, there's a space between it to get to B. Some arrays like that, especially if it has a fixed structure, if it has a variable structure, there's other ways to doing that. But what that doesn't, that's not so important here. The idea here, though, is that you have a data structure that's about having data in lists one after each other. And you can also have arrays of arrays, and then you can continue with that to have more dimensions of this structure. Oh, so, hold on. So what are the advantages of arrays? So first, this goes for easy indexing, I should say. You can easily access elements by their position. It's usually a straightforward mathematical equation to figure out where to get the nth element of an array. It's often memory efficient. Contiguous allocation can improve the performance. Sometimes you can even be able to anticipate what the data actually is because it's in order. And it's ideal for scenarios where order matters or when random access is frequent. That's why you'll see like RAM itself, random access memory, the information there a lot of the times is ordered or is stored in an array, or at least arrays are used as one of the data structures in order to implement random access memory. So now there's the second category. You have dictionaries, objects. Sometimes you'll hear them as hash tables. The concept of here is key value pairs, like a real dictionary word lookup. You have instead of numeric indices, you define the keys. You define how you access that data. And it's flexible. You can attach descriptive names to data elements. So for instance, dictionaries for real world models can represent a complex entity like a person object with keys like name, age, and height. So sometimes they look a little something like this, right? So let's say you had, you had a person, right? You have a person here. Sometimes it would be represented. I mean, this is, let's just say this is language agnostic, but you'll see something like this and you'll see, oh, okay, fine. Name equals, let's say, okay, I'll write my name, right? And then you'll see age equals 39, right? And then you'll see height equals, let's say, we'll just say do it in inches, 74 inches, okay? So you have this person, and then you have these three keys here, name, age, and height, and I can directly reference the values, K or 39 or 74, by saying, let's say in a lot of language, person.name, person.age, person.height. But the idea here is that I'm accessing this stuff not by numbers, but by actual letters or actual names or whatever it is that I want to identify it with. And this gives us the ability to give your own specific name to a value has, again, it's another valuable tool here. So sometimes, having it by index or where they are stored is important. Sometimes you really want to have that name because one of the benefits here is that person, like this person object or dictionary, can represent an actual person, and you can have a number of different people that have name, age, and height characteristics. So there's no need to remember integer indices. You can extend objects with attributes and related data easily when you do it this way. All right, so now we're going to the third category, trees and graphs and things of that nature. These are data points connected by relationships rather than positions or keys. Notice that you have arrays, positions, dictionaries, objects, like keys. Now we're talking about relationships. The data itself, the relationship between one point of data to another point of data is important. The canonical examples, you think of social media, right? Like everybody has friends or followers and so on and so forth. People are connected to each other. When that connection is important, trees and graphs become something that's really useful. So trees, you have like a hierarchical structure, like a family tree, but in graphs, it's like more general connections because a tree is just a specific kind of graph, like networks, social graphs, linked documents, and so on and so forth. So the power of trees and graphs is that they can model relationships and dependencies and efficiently represent connected structures like routes on a map, enable complex queries based on connectivity rather than just order or trees. And again, when it becomes easier, I'm just going to draw a little something. Then again, with the friend idea is that if I have like, let's say this person one over here and person two over here and person three over here, right? And I want to represent that person one is friends with person two and person three is friends with person two. I can make a connection like that, right? And let's say this connection line means friend, right? Excuse my chicken scratch, but you can represent that here. And now with these two connections, you say, oh, P1 and P2, they're both friends of each other. P2 and P3 are friends of each other. Are P1, P3 friends? Well, there's no line between them, so they're not. This is more accurately or more efficiently represented in a graph, because what's important in here, the highlight of this data structure is the connections between the data points. All right, so let's move on. So comparing the three categories, you have arrays and lists, order sequences, fast indexing, simple structure, focusing on position of data in order to get and retrieve data, right? Dictionaries and objects, key lookups, descriptive data modeling. The focus on there is to be able to have name keys to get specific data. Trees and graphs, relationship-based, complex connectivity, flexible representations, focuses on understanding the relationship between two or more pieces of data. That and this, and like that's how you can, like, this is one of the, like, again, one of those like areas of intuition that you start to see patterns about like what is important for the data to have. Is it important for me to be very efficient in laying it out and it's ordered? Is it important for me to be able to have a named thing to get to a particular piece of data? Is it important for me to know the relationship between data? This is why I use one data structure over the other. The common thread, though, is that all structures store and manipulate the same basic binary data. Again, everything's fundamentally still zeros and ones. It's just that choosing the right structure depends on the type of data you have, the operations you need to perform, lookup, insert, traverse, who knows, and the patterns of data relationships. So, and then moving on to efficiency and scale, the proper selection of data structures ensure faster responses at scale, like as your system is being used more and more to be able to handle that scale. The proper data structure can really help with that. Better use of memory, because memory is not infinite, and more intuitive code and system design. Again, the right selection of a data structure can simplify a system tremendously. And the goal of system design is to produce and to have the most simple system design that fulfills the requirements, because the more simple the design, the easier it is for people to be able to use it, maintain it, build it, and so on and so forth. So now here's it. I'll have different points talking about gaining intuition, recognizing the patterns in data storage. You see the three categories. Grouping them in these three categories helps, because when we start to get into a number of case studies about how you can design certain systems, you'll notice that, this data structure in this context seems to have this effect, and I can use that in all these other system designs as well. It seems like three of those case studies that we went through, and a case study, I call a case study, is one of the applications that we're going to design in the next section of this course. They seem to be having the similar ability to do a similar thing, and you start to understand the connection between one and the other. This is how senior engineers are able to look at a new problem, and it's like, oh yeah, this is how I do. I should do it this, that, and third, because they have this intuition of what data structures would be best employed to execute to build a system of that liking. So understanding how arrays, dictionaries, and graphs influence system architecture, as I mentioned earlier. And this intuition helps you design robust, maintainable, and efficient systems. So, next steps in future lessons, we'll see how to use these structures with tasks, which again, zeros and ones, but are focused on executing instructions from the CPU. And we'll explore how combining data storage with well-chosen tasks leads to these building blocks. Keep thinking about how data is stored and why it matters. Thank you so much, and I'll see you in the next lesson. This was from my original course on system design for junior engineers. Since then, I've refined and expanded everything you just saw into the full system thinking and AI era course, using these same building block principles across 15 plus real case studies. If this resonated with you, the link is in the description.